One more new thing to show you about systems of two equations. And here's a problem. Solve 4x minus 8y equals to 17 and negative 6x plus 12y equals to negative 11. So where should we start? X's are smaller, so how about we eliminate x? So I'm looking at 4 and 6, and the least common multiple of 4 and 6 is 12. It's kind of like finding, again, sort of like finding a common denominator. If you're adding 1 4 plus 1 6, then you would use 12 as your common denominator. In this context, you would say it's the least common multiple. Alright, so if I multiply the top equation by 3, this will give me a 12. And if I multiply this by a 2, that will give us negative 12. So let's see what happens here. I'm going to get 12x minus 24y equals to 51. Down below we've got negative 12x plus 24y equals to negative 22. So look what happens when we go to add. Not only does the 12x term cancel, but also the 24y term cancels. We haven't succeeded in eliminating both x and y simultaneously at the same time. So what's left on the left side? It's not the great void, it's 0. These numbers cancel, literally giving you 0. On the right side, we get, whatever that is, 29, I believe. And now what? I have nothing else to solve for. And matter of fact, I ended up with something impossible. 0 equals to 29. So I'm going to declare this to have no solution. You need to write a conclusion to convince me that you know what you're doing. So put a conclusion, but I want to see how you got that conclusion. By eliminating, in this case, x and y's eliminated, then we ended up with this impossible situation, 0 equals to 29. Alright, well, there's a lot to talk about here. And the first place people really confuse this is in checking their work. If you're checking your answer to a problem and you get something impossible, then you've got a mistake. It's when you're solving and your variables eliminate and you get something impossible, that's when you have no solution. And so no solutions come from attempting to solve an impossible problem. Wrong solutions come from having the wrong numbers after you have solved it. So you're going to need to keep that straight. All right? And as to that difference. Now, another textbook sometimes label this situation inconsistent. And it would be perfectly fine to me if that was the word you wrote for a conclusion. The system is inconsistent. That's an acceptable mathematical term. I kind of prefer a more down-to-earth answer, no solution. All right, but inconsistent is okay. What causes this, and is a good question to ask, and it's really quite simple. What about the two lines? Think about this in the graphical sense and the geometric sense. And it turns out that when we alter these equations, we produced lines which are virtually identical except for the right side. And it turns out that means that they're running parallel. They would have the same slope. So you could go through, solve for y, and determine that the slope of each equation happens to be 1/2, just visualizing it. So here's visually, or geometrically, what happened here. This equation is, oh boy, what would that be? Negative 17. I think it goes something like this. All right, I'm not too worried about the specifics of where the graph is, but it can be seen that the slope is 1/2 if you worked it out. All right, so let's humor me. Suppose that this line is the equation, is the line representing that equation. What about this one? That equation runs parallel to it, and I'm not sure exactly where it goes. Suppose it goes down here. And so, we've seen this before. Parallel lines do not intersect. They don't intersect. Now, lines only intersect in one place when they do intersect, because they run straight. And so sometimes we get, usually, most cases, we get a single solution, because the solution is the intersection of two lines. There's one answer. But in the parallel case, it's impossible to solve. And I think the wonderful thing about this is that the algebra confirmed it. That if these represent parallel lines and the solution is intersection of two lines, it's impossible to solve geometrically. And the algebra bore that up. When we tried to solve, we got something that was impossible to deal with. All right, there's one other situation, and let me just quickly give you it. Suppose your lines were the same. So here's a new problem. Solve x plus 2y equals to 3 and 2x plus 4y equals to 6. In this case, you can see, I think rather easily, that the second equation is precisely 2 times the entire first equation. And so really the second equation comes from the first equation by multiplication. If we were to attempt to eliminate variables here, we would get something like this. We would end up with 0 equals to 0. And which is always true regardless of what numbers solve these equations. And so your textbook has a couple of these hidden, sprinkled throughout there. These, I like to call these no unique solution. And if you call it no solution, I think I'd let that pass, but no unique solution. Books call this, more technically, they say this is a dependent system. And sometimes they'll ask you to solve for y in terms of x. I'm not going to go that far. It turns out that when you have larger systems of equations, more variables, when you run into the dependent situation, from a mathematical standpoint, that's actually very, very interesting. And so you would have to study math at a considerably higher level. I think when it comes to two lines being the same line, one line literally is lying on top of the other one. So each, there are infinite million solutions. I think with two equations that are dependent, this is a very boring situation. It's not very interesting at all. But on larger scales, dependent situations are actually quite fascinating to work with.